We want to cluster the grades after an exam. For this we create a histogram, and we see our histogram has two peaks, so we try to fit a Gaussian mixture model. The Gaussian mixture model takes three parameters that we can infer from the data using the EM algorithm. Now we want to implement this in Python. Hi, welcome to a new video. Today we want to implement the Expectation Maximization Algorithm for the Gaussian mixture model. And for this we will use the derivations that we did in the previous video, and we have our summary here so that we can hand it over and quickly implement it. Okay, let's start with first importing the necessary packages, and we first import a package in order to suppress TensorFlow warnings. Then we need NumPy, and we use NumPy because we will implement the algorithm mostly in NumPy. Still, we will use TensorFlow Probability. So we first need TensorFlow STF, and we need TensorFlow Probability. And we will use this to create our data and just for some convenience later on. And I will also implement TQDM. TQDM is just a really simple progress meter that allows us to be a little more visual on what we're doing. Okay, then let's start. First, let us create a main routine. I will leave this empty at first because then we can implement the switch that our file is only executed when it is run in the Python interpreter. Okay, then let's start with our main routine, and we first have to create a dataset and define the constant values that are relevant for the expectation maximization algorithm. Of course, if you have your own dataset that you want to cluster, then you will use this. But here, for the sake of simplicity, we create a data with a mixture model, and then we try to infer the parameters again. Okay, first I will start with the class probabilities, and I will call this true because this is the true values of the generating model. And we looked at the distribution of grades, and the two clusters that we're looking at are the students that failed and the students that passed, or the other way around. And let's be fair, let's say 60% of the students passed and 40% failed. And then we have to define the mu's, or the centers of our distribution. And the passing students are centered around 2.5, and the failing students, let's say, are centered around 4.8. And for the passing students, we have a wider Gaussian, let's say 0.6, and for the failing students, we have a 0.3, as this is a really narrow Gaussian, because mostly, at least in the German grading scheme, you fail with 5.0, so this should be around the 4.0 really narrowly. Okay, then some other parameters that we need. We have to define a random seed. Let's put this to 0.42, and this is for reproducibility. Then we need our number of samples that we want to sample from our model, and for here we start with 100, and the number of iterations for our expectation maximization algorithm. And for debugging purposes, I will start with 3 first, and then we will increase it later on. So then we can generate data. And we, for this, create a Gaussian mixture model by the help of TensorFlow Probability. So I will call this univariate Gaussian mixture model. And this will be a TensorFlow distribution mixture, same family. And this takes two arguments. First, mixture distribution, which will be categorical with the probabilities according to the class probabilities, or the true class probabilities that we defined, and a components distribution. And for this, we will use a batched normal distribution, and we provide it with the location, and the location are the true mu's, and the scale are the true sigmas. And then we can create our data set, which will be sampling this distribution with the number of samples. So we do a univariate gmm.sample, and we sample the number of samples. And one important aspect, this will return a TensorFlow tensor, but since we want to work in a NumPy world later on, I will just convert it into a NumPy array. And then let's look at the data set at first before we start implementing the EM. Then we can see let's bring the terminal up here. Let's call Python on our script. And we see we have a typo here, so let's put this in, try it again. And great, here we have a data set and we see there are grades distribution, the student that got a 5.0 and so on and so forth. And from this we will infer the parameters again. Okay, then let's start creating the interface for the EM algorithm. And the EM algorithm depends on the data set. It depends on the number of classes that we want to find in our data set, or the number of distributions. And then we have the number of iterations, and it needs a random seed. Okay, before we implement it, let's call it from our main routine. And of course, we also have to define the number of classes here, but this is in accordance to the length of our array here, so it will just be 2. Then we can comment this out and call our EM algorithm and provide it with the data set, we provide it with the number of classes, we provide it with the number of iterations, and we provide it with the random seed that we just defined. And the EM algorithm later on will return us with the class probabilities, the mu's and sigmas. And then we have our interface down, and we can also already print them out. So we have the class probabilities, then we print the mu's, and we print the sigmas. Fantastic. Okay, let's go back to our main objective here to define the EM algorithm. And the EM algorithm, for this we first have to infer the number of samples from the dataset. And the dataset is just a one-dimensional array, so a vector. So we can just use dataset dot shape, and we need it in the 0th dimension. This will give us our number of samples. Then let's do the random seed, NumPy dot random dot seed. For this, we can just be sure that our algorithm is reproducible. Of course, you could also just leave this free and you would get a different result each time. Let's discuss this at the end. Okay, first we have to start with the initial guesses for the parameter, or for the parameters. And first, let us define the mu's and the sigmas. So the mu's will be just a random vector of this n classes. And this will return a vector with 2 components in our case, with values in between 0 and 1. Then for the sigmas, we do the same strategy. And this is fine because the sigmas have to be positive, so we adhere to this constraint already. Then we can define our class probabilities. And for the class probabilities, it will be a little more difficult because we can't just use random, because in most cases, then our class probabilities wouldn't adhere to the property that it has to sum up to 1, because they are the probability of the categorical. So we use the Dirichlet distribution and feed it with a vector full of 1s that is of size of the n classes. And by this, we are getting back a vector which is also random, but it adheres to the probability that it has to add up to 1. Okay, then let's start with our iteration. So we do for EM iteration in the range of the number of iterations. We do the E step and the M step. Oh, there's a typo. And we can also wrap this in our TQDM in order to make it a little more visually appealing. And now we just have a neat progress meter. Okay, let's start with the E step, and I will bring over my cheat sheet here, and we have to create I have to calculate the responsibilities, and the responsibilities are a matrix of size number of samples and number of classes. So let's allocate them. So these are the responsibilities, and I will just use a 0 matrix filled with zeros, and it is of number of samples, number of classes. And that's great. Then we can fill it. Let's iterate over the rows and the columns. So let's say for I in range of n samples, for C, let's call it the class, in order to adhere to our naming scheme. And then we can fill them. So we have responsibilities at I, j is equal to the class probability at the sieve class times, and I go into the next row. And then instead of writing this expression down, we can just resort to using TensorFlow Probability, and we use TensorFlow Probability distributions.normal, and the location is our muse accessed at the C class variable, and the scale is our sigmas accessed at the C, and we just query the probability at the ith dataset point, and by this we get the same as if we would write down the exponential. Of course, we have to normalize our responsibilities, so we divide them by the row norm, and I will use the divide equal sign, and then we divide it by NumPy linalg norm, and we get the norm of our responsibilities over the first axis. So by the first axis, it is meant the axis over the classes, and we have to get the one norm, and we want to keep the dimensions, otherwise our shapes will not coincide anymore. Okay, and then we do the first step, we calculate the class responsibilities. They are nothing else than summing over all the samples, and so we do numpy.sum over the responsibilities and over the 0th axis, as this is the axis associated with our samples. Great, that's our E step. Let's go on with the M step, and we see for all the steps in the M step, we have to update the components for each of the class. So we can just handily iterate over all the classes for C in range of n classes. Then let's start updating for the class probabilities. The sieve entry will be updated according to the class responsibility at the sieve component divided by the total number of samples. And the muse will be updated according to muse of C is, and then we take the summation of the responsibilities at the given class with the dataset and then sum over the samples. So we do summation over the samples, and we multiply the responsibilities at all the samples and the given class with the dataset. And we take the sum over, well, there will only be one axis left in the end, so I can also remove this, and we take the sum over all the axes. And we divide this by the class responsibility of the sieve class. Then let's go on. Lastly, we have the sigmas, and let's look at a cheat sheet here. And for this, we have to take the square root and the square root of the summation, and we divide the summation later on by the class responsibility. But here this will be a little more tricky, so we have to do some sort of like component-wise multiplication and exponentiation. I will write this down, then I will explain it. So we do the responsibilities of any sample and the class C times the data set minus our updated mu in brackets squared, and we sum over all the x's because there will only be one axis left. And then lastly, we divide by the class responsibilities of the sieve class. Okay, let's look at what is happening here. The dataset will be the vector, and a muse indexed at C is just a scalar value. Then we have some broadcasting happening so that we subtract from all of the components in our dataset. That makes sense because we subtract from all of the components in the dataset the one mu that's associated with class C. Then in brackets we square it, makes sense, and then it's a component-wise multiplication of all the n samples with all the for all the n samples responsibilities and all the n samples that we have in our augmented data set, and then we sum up. That is what the NumPy sum does, and we divide by the class responsibility, take the square root. Fine, works. Okay, then let's return the stuff that we found. So we have the class probabilities, we have the mu's, and we have the sigmas. And then let's get into our terminal and call the EM algorithm. And we see it creates a data set, and then it starts our iteration. And I will move this away so that we can take a look at the true values and compare them with what we found. And we see we found the class probabilities to be 0.51 and 0.48, so they're quite close actually still, but we have some sort of a better separation in the mu's here. Also take care, the order might not necessarily be the same, because I mean, you can have the Gaussian mixture model the other way around, it will still work. And in this case, indeed, we found it the other way around. And the others are a little bit off. But this makes sense because we only have 3 iterations. So if we boost this up to 10 iterations, for instance, and let this run, then it runs for the 10 iterations with this nice progress meter, and we see, oh, we're getting a better separation. Oh, this is really nice. We have 0.6 and 0.4 really nicely covered. The 4.8 and the 2.8 are also nicely found, and the 0.3 and the 0.6 also works fine. And of course, we can improve this when we give it a little more samples. So if we go up to 1000 samples, so then our data set is more representative for the distribution. So it was like a really big exam that 1000 students took. And then we see, oh, this runs forever. And in order to make this run in a reasonable time, there's one really nice trick. And for this, we will go into our EM algorithm. And here we have a double for loop. And this is, if you profile the Python code, then you will see that this is really like giving us headaches in the performance. And we can improve on this by using a batched normal that is then applying to a broadcasted dataset. Okay, this sounds crazy, but let's get this down. So instead of defining the responsibilities as the 0 vector and then filling it, we will just create it by the call to our, I have to get the naming right. Yeah, seems fine. And we just call it by our batched normal. So what we do is we do tfp.distributions.normal, and instead of providing it just with one mu value, we're providing it with all the mu values for the location, and also with all the sigma values for the scale. And then we query its probability on the data set, on the entire data set. And what it does, it should, in the best case, return us with this matrix that we created with the double for loop earlier. However, and we can try to run it, and we will run into a problem of wrong broadcasting. Yeah. Oh, of course, we also have to make sure that we type it correctly. But we will run into a problem with broadcasting. And we see incompatible shapes. And the problem here is that our dataset, of course, has 1000 entries, and we have a batched normal with 2 entries. And in order to resolve this, we have to reshape it into a matrix, but only with 1 column. And we do this by -1, 1. This will just be a matrix with a really long column. And then, of course, we want to work in a NumPy world. So also let's return this as NumPy. And now our implementation should work fine. Theoretically, let's hope for it. Fantastic. And have you seen how fast it goes? Like it is a major difference. And we see we are converging at our results way better. And we can also increase the number of iterations easily because now it runs extremely fast. And after this, by the way, the first startup is due to the fact that we create the dataset, and the actual algorithm is way faster. And we see we have really, really good coverage. So For our perfect data set, we are getting really close to our original values. Okay, that's the implementation of the expectation maximization. I hope this made a little more clear and hope that gave the hard derivations more sense. Feel free to post a comment if something is unclear. Here you'll find similar videos. See you next time.